molecules are perfect by themselves, it turns out, right? Otherwise, our life will not sustain.
Right.
Molecules are perfect. We just don't know how to make them into a crystal as perfect as silicon or germanium.
Okay.
So that's something that we started working on.
2D electron transport has been an important topic in science and technology for decades. 2025 David Turnbull Lecturer Jiwoong Park is at the forefront of research in this area, and he's here in the MRS TV studio with us now to tell us all about his work. Such a pleasure to have you with us today.
Thank you so much for having me.
Certainly. This is a really exciting topic. I want to get started with kind of, if you can explain for us why 2D electron transport has been such an important topic recently.
The topic itself is not new. What I mean by this is that inside of your cell phone, you have a bunch of transistors. Now, these days, everyone is talking about transistor all of a sudden. It turns out the electrons are moving in 2D. What I mean by that is that there is an interface or kind of surface that's hidden inside of your transistor. Electrons are moving around on that flat surface. So electron transport for transistors, that's moving XY, not in Z, that has been for decades.
Okay.
So that's what all our information technology is built on. Now, surprisingly, all of that amazing thing has been done with three-dimensional material, like bulk crystal of silicon at the top surface, right? What you can quickly realize is that the rest of the crystal, except the top, few layers of atoms, is just there. So wouldn't it be very interesting if you can make very good crystal that's only very thin, right? And so that's the beauty of two-dimensional crystal. And so, that's what's exciting a lot of people.
And so to kind of zone in on that, how have the recent advances in the 2D Vanderwaal crystals helped you advance your research?
Let me take a step back, and then it turns out that a lot of previous research in material science, we develop a lot of materials first, crystal. And silicon needs to be made in a big crystal so that you can make a bunch of transistors that we are using. It turns out that 2D crystal, or the field of 2D electron transport, was really motivated by Nobel Prize winning science that was done decades ago. And that's led by Andrei Geim, Novoselov, and so forth, and my friend Philip Kim. And so that phenomena was discovered, based on very amazing technical exfoliation. Now, since then, for a couple of decades, people really wanted to do that in big scale, right? Doing this in a small crystal, that's great, it's fun, but we really want to generate things in a big scale so that people can turn them into chips, devices, cell phones, etc. And so a lot of efforts have been made to make big films of only few atom thick semiconductor that you can use. And so that has been something that really powered a lot of people's research in the past couple of decades, including my own.
All right, and so I mentioned you are this year's David Turnbull Lecturer. Let's talk a little bit about your lecture. You're going to be focusing on the magic of 2D crystals. What is so magical about them?
Thank you.
Yes, big congratulations on your recognition.
So I need to shrink 40-minute lecture into few minutes.
Right.
Now, I love the word magic. So I want to define what magic is. Magic is something that's really seemingly impossible, right? Just rabbit coming out of a hat, but physically possible. That's what magic is. And so what we really want to discuss in my lecture is so many different magical ways that these atomically thin crystals allow you to realize fascinating properties that are seemingly magical, impossible. Electron transport in 2D, electrons moving in XY, but not in the vertical direction. That's one magical properties, but there are other things. For example, what I'm going to talk about is how to make heat move on the plane, but not vertically. That's
Okay.
interesting.
Very interesting.
Yeah, I mean, it'll be great for cooking, for
Fascinating,
example.
yes.
Because you want to make a really hot plate, but
Yes.
the bottom is served. Cool.
Uh-huh.
It turns out that 2D material allow you to do that, right? So, a few years ago, we reported a fascinating phenomena where heat really moves XY direction 1,000 times better than vertical direction.
Okay.
So to vertical direction, it's as insulating as air. But in the plane direction, it's as conductive as steel for heat.
Okay.
So that's interesting.
Yeah,
How can that be
fascinating.
possible? Or another thing that we are talking about is, can we make light move in XY direction freely, but not in G direction? And again, that's 2D photonic transport. That's something that we try to realize. So my main thesis is that there are a lot more magical properties that you can study beyond electronic 2D transport, even though that was the beginning of all the amazing things
Right.
that people are now studying.
That was the origin. So to kind of zoom in just a little bit, can you talk a little bit about your latest work in engineering novel molecule inorganic hybrid 2D systems?
Yes.
Can we get specific there?
Absolutely. So I'm just fascinated by this. It goes all the way back to about 9-10 years ago when I moved my research lab from Cornell University to Chicago. And it's a really exciting new environment with a lot of tradition. And so we thought about new problems. Okay, molecules are perfect by themselves, it turns out, right? Otherwise, our life will not sustain.
Right.
Molecules are perfect. We just don't know how to make them into a crystal as perfect as silicon or germanium.
Okay.
So that's something that we started working on. It's not only academically and intellectually fascinating, but at the same time, practically and scientifically exciting. The reason is that molecules, they know how to put everything within themselves. That could be electron, or that could be what happens after light, right? Light gets absorbed and then light comes out. It's a quantum material too, by itself. So by turning them into beautiful crystal, we can actually use molecular films for practical purposes. So that was the thesis that we had. We just did not know how to make molecular crystalline film. And so that was the big idea that we started working on. It took, I don't know, almost a decade for us to publish papers of this. So this year, finally, we published 3 papers, so we are so excited.
Amazing. Well, so looking ahead to the next decade, what's next for your lab?
That's a good question. I should ask my group about this. I would love to continue what you are doing. I would say that in the past couple of years, what the field, and that including my group, prepared for is really building wonderful building blocks. What I mean, building blocks is a kind of a overused word, but in this case, I really mean it. I should say maybe building papers, right? Because it's a 2-dimensional material. We would love to turn them into devices and structures that is just remarkable outside of our imagination. A few decades ago, we started a project that we paused for now, but we might resume, to make circuits that can fold, unfold, fly,
Wow.
and then go and swim.
Okay.
Why don't we work on that? It turns out that the biggest problem is that 3-dimensional materials like silicon, germanium, it's really hard to do it. It's either too granular or it's too rigid. But we know, from our experience, thin papers, if you fold it, cut them well, then you know how to fold them, and then you make a pop-up castle,
Right.
right? And combine them with a little bit of actuator, meaning small motors or muscle, one might be able to generate stuff that does what living forms can do. And so combination of such high-performing circuits with high-performing muscles could be really exciting object that we can think about. So that's one example, but
Right.
there could be other topics that more creative people can work on in the future.
Right. Well, it'll be very exciting to see what the next 10 years holds for you and your lab. And again, congratulations on your recognition. Best of luck in your lecture today. Thanks for your time.
Thank you so much.